Hi everybody, and this is just a quick video to overview what's going to be in the reading and to build off of where we left off of at the end of class. So we talked a little bit about electric field already, and I know you learned about it last year, but I wanted to emphasize a few key points. So the first is how we deal with the equations that we use in order to calculate electric field. So if you remember, I showed you a version of this picture in class. When we're talking about a field, we have a source charge that creates the field, and then we have a charge that's placed in that field and interacts with it and experiences a force. In this case, A is the source charge, and B has been placed in A's field, and it feels a force. Let's build off of Coulomb's law and sort of define what we call how we use the electric field produced by A. So let's say at the location of charge B, which I actually have over here, I've removed B and just talked about its location without B there. Because with fields, remember, you don't need a second charge. The source charge affects the space around it and produces that field whether there's a second charge there or not. So at point P, we have an electric field. Let's say it's called capital E. And so if I have that electric field at point P, were I to come along and put a charge Q, in this case it's QB, at point P, it would feel a force. And so the fundamental definition of electric field is that the force that A would exert on B through its field is going to be the electric field produced by A times the charge of QB. So I'm going to label B as little q. A I'm going to label as big Q because it's the source charge. And that electric field, we just have to know that it's the field produced by A, and then little q is the Q that's represented by charge B. So that's the definition of electric field. If I have a field and I know it and I put a charge Q in it and I multiply the two, I get the force. Electric field is defined as newtons per coulomb because when I multiply by coulombs, I will get newtons over here. Okay, so that's our basic definition, kind of like weight equals mg, similar kind of idea, right? We have this little way to calculate force on a charge if we know the field. But what if we don't what if we don't know the field? How do we figure that out? So we can go back to Coulomb's law, which is that the force of A on B is equal to K times QA times QB over the distance between them squared, which I'm just going to call R squared. So that's also a way to represent the force that QA is exerting on QB. And now just by equating these two equations, I have EQ equals K big Q little q over R squared. I can cancel my Q's, and I get an equation for the electric field produced by charge A, which is equal to K times the source charge over R squared. Now, just like Coulomb's law, remember, in this we didn't use the charge signs, we just used the magnitudes. Same thing, there's no signs when you're calculating electric field. You don't use the signs of the charges. Now, it's important to note that F equals EQ. That's a general definition. If I know E at a point in space and I multiply by the Q that I put there, I get the force that Q feels. I can always use that. This, however, was derived using Coulomb's law, which is true for point charges. So this is actually the electric field of a point charge, Q, which is KQ over R squared. So it's the charge if it's an infinitely small point. Now, we can also use this if we're outside of a shell, because the shell, as we talked about today, acts as if it's concentrated as a small point. But you'll see soon that we are going to want to look at the fields of other kinds of things. Like, what's the electric field? You know, if I have a sheet of negative charge, what's the electric field above a sheet of negative charge? What's the electric field some distance from a ring of charge? What's the electric field if I have a line of charge somewhere over here? So we can have actually physical distributions of charge that are not point charges. We'll find that we're going to come back to this fundamental definition in order to figure these things out, but know that this equation only applies to a single point of charge. Okay, next slide. Here's an example of something that's not a single point of charge. It's two parallel plates which are made up of collections of points of charge. We will eventually be able to prove that the electric field between these plates is as it looks, which is constant. So we have these electric field lines that are actually all uniform, all pointing from right to left, and we can tell that it's a constant field because the electric field lines are all the same spacing no matter what. You'll notice when we had the electric field due to a point charge, for example, a positive point charge, the electric fields are denser if you're closer to the charge, and they're less dense if you get further away. So the density of the field lines actually determines the strength of the field lines. It's a great representation. For parallel plates like we have here, the field lines are all uniform, and we haven't really proven it, but it's constant. So this is a great way if you want to create a constant electric field E in space, you set up some parallel plates. Okay, so here we have two parallel plates and we're shooting an electron into the plates. We want to talk about what's going to happen. So electron is shot between a pair of parallel plates with an electric field E between them. Sketch the path of the electron as it moves between the plates. Assume the velocity is fast enough that it makes it to the other side. So if you want to sketch the path, you might say, well, how come it just doesn't move straight across? And that's a good question. It would if there was no electric field. It would just, if we ignore the effects of gravity, it'll just move straight through the plates. But that electric field is going to cause a force on that electron. And the electron, just by looking at the signs of the plates, is going to feel a force in this direction. And there's two ways to analyze that. Once the electron's inside the plates, it'll be attracted to the positive plate and repelled by the negative plate, so it'll get pushed to the left. Another way to think about it is that the field lines all point to the right, but that's telling you how a positive charge would go, and since an electron is a negative charge, it'll go the other way. And we can even go a step further and say that the force the electron would experience is going to be equal to E, the electric field between the plates, times Q, which remember for an electron we use lowercase e for the electronic charge, and that's going to be in the negative I hat direction, so it's to the left. But the force in the j hat, or the upwards direction, is 0 because there's no force exerted on it. So if I have something moving in the j direction, as the velocity initial, is going to be 0 I hat plus some v naught j hat. What's going to happen? It's going to be pushed and accelerated downwards, to the left, in response to this force. And in fact, if you guess, the electron is going to curve downward, you were correct. So here's a picture of the path of the electron. We can go a step further in analyzing this and think about the fact that really, what is the shape? It looks parabolic, but is it actually parabolic? Well, we know that EE is the force on the electron, and that's going to be equal to the mass times the acceleration in the x direction. And we also know that acceleration in the y direction is 0. Let's just x, y. So our acceleration is going to be in magnitude E over m. But remember, the electric field is constant. So this is actually a constant acceleration. So if I were to turn this on, where else have we seen something that has no acceleration in one direction and acceleration in the other direction? And the answer is when something moves in a gravitational field. If I shoot a particle out in gravity and I allow it to fall, remember I have a constant force of gravity acting down, and then I have F equals 0 in that direction. And so the combination of motions creates a parabola. So in this case, it's the same thing. My electron in the direction opposite the field, in this direction here, has an acceleration. But in this direction, it has no acceleration. And so it is indeed going to follow a parabolic path. And in fact, you can use the big 5 to figure out its trajectory. Okay, just a quick summary here. Important things about the electric field. It's defined as the way a positive charge would go in space. It's represented visually by field lines. Denser field lines mean a stronger field. It's a vector. Because it's a vector, you don't use the signs in the calculations. You only use the magnitudes, and then you figure out direction by looking at the situation. When you have more than one source charge, you determine the electric field produced by each separate source charge and combine the vector. So if I have two things on opposite sides of me pulling and pushing me, just like with forces, I do each one separately and then combine them. And as you know, symmetries are your friend. Sometimes you can avoid a calculation by noticing a symmetry. Finally, summary of the two equations. So this is the force on Q. This is the E that's not produced by Q. It's produced by a source charge. And then this is a charge placed in the field produced by something else. This electric field can be caused by a single point charge, like it was in the case with the particles A and B, or it could be caused by an array of charges like parallel plates or something else. It doesn't really matter. If you know E and you put a Q in it, you can get the F. This is a very specific equation. If you have a single point charge or a shell of charge that's acting as if it's a point charge, for example, Q, you can get, sorry, this should say E, the electric field some distance from it, a distance r away, using this equation. So that's if I have a charge Q and I'm at a point P, a distance r away, what's the electric field? This is how I do it. If I have charged plates, let's say this one was plus Q and minus Q, I can't use this to figure out the field in between. That's a different geometry. This only goes with this geometry. Okay, I think that's everything I wanted to say. That'll summarize the reading. Hopefully it's helpful, and I will see you guys on Thursday, where we're going to take this and use it to calculate the electric fields of wacky objects. Okay, bye.